Controls. We are a Mid-Atlantic employee-owned automation and robotic solutions provider. We are also an automation technology center with 3 certified automation specialists and 1 motion and drive specialist. I am one of those certified automation specialists, and that's why I'm hosting the webinar. I will give you my contact information at the end of the webinar so that you can have my email and phone number. Because we have a bunch of automation specialists that are specialized with Siemens, we have consistently achieved an elite status with Siemens for that. So here's the scope of the webinar. We're going to speak about the global memory areas and data types in the PLC. We're going to talk about how the Siemens PLC scan cycle functions, and then we're going to hop into all of the relay ladder logic instructions. Sorry, I can hear somebody. We're going to hop into all the relay ladder logic operations, and I'm going to explain each one of those. We're also going to have the opportunity to talk about organization blocks, functions, and function blocks. So I wanted to start the conversation out by talking about global memory area with Siemens PLCs. So you have your I memory, your Q memory, and your M memory. And if you see in this graphic here, you can see that for the I and Q memory, each one of these is a single byte consisting of 8 bits. For the I and Q memory, you can have up to 1023 bytes. And for global memory, which is the M memory, you can have a significant amount more of byte of information. And you'll kind of understand how this works as I break it down, but I more or less want to explain how data types translate from bytes and words and double words of information. I'll also explain a little bit more once we get to the scan cycle, the importance of I, Q, and M memory. So for those of you that are not familiar, a byte of information consists of 8 bits, the least significant bit being the far right and the most significant bit being on the far left. So the notation would go 0, 1, 2, 3, 4, 5, 6, 7. Now, for those of you that are not familiar with this, you may be wondering, how does someone get a decimal or numerical value from a byte of information that is just a bunch of ones and zeros? Well, the answer is pretty simple. If you have a value of 1 in this portion, this bit of this byte, the mathematical term of doing it would be 2 to the 0 would be 1. If you had a 1 here, 2 to the 1 would be 2. If you had a 1 here, it'd be 2 to the 3 is 4, and so on and so forth. So if you have this byte of information that has a whole array of ones and zeros in it, any value or slot that has a 1 will be calculated and then added together. So in this instance here, this byte and these last 4 bits, which would relate to the numerical values of 16, 32, 64, and 128. In this instance, you would add up those 4 bits and their numerical values, and that would give you a readout of information. With a byte, because you can have up to 8 bits, the values range from 0 to 255 if you had all ones in this byte. The step up from a byte is a word. A word is essentially 2 bytes, as it says here. Now the notation's backwards for labeling the bytes. And what I mean by that is this is byte 0, this is byte 1, but this is the this is the least significant bit, and this is the most significant bit. Now, because you have an extra byte of information in a word, your values can go even higher, and in this specific instance, you can go from 0 to 65,535 if you had a full word of information filled with ones. Next step up from that is an integer. An integer is essentially the same size as a word. However, the last bit, the most significant bit of this integer is not a numerical value, it holds the sign. So because there is a signed value for an integer, you can't have 0 to 65,535 like you would have with a word. That last value becomes a positive or negative, which gives you a bipolar value of negative 32,768 to 32,767. So like I said, word and integers, they both occupy 2 bytes, 16 bits. A word is unipolar, 0 to 65,535, and an integer is bipolar and can have a negative value. The next step up from that is double words and double integers. Essentially, in terms of calculating or having a range of data. It works the same way, except now you have an extra word of information or another integer of information available, which gives you a larger range of values. So in this double word, sorry, I get a lot of feedback from somebody. If you could please mute yourself, that'd be great. Thank you. Oops. So like I was saying, with the double word and integer, essentially you have another 2 bytes of information. So those values that value range increases. You'll see here for a double word up to 4,294,000,000, so on and so forth. And then for double integer, it's bipolar. So it has the negative range and the positive range. Now, there's also real numbers, which also occupy 4 bytes of information. And in this instance, byte 0 is the exponent, and then bytes 1, 2, and 3 would be the mantissa, which is this value here. Now, you may be wondering, how do those data types relate to I, Q, and M memory areas? So I'm going to show you this in the user program in a second. A bit, and you can interchange this M with an I or a Q, and I'll explain that the difference between I, Q, and M in a second. But addressing, for this specific example, a bit is M memory bit, or sorry, global memory byte 0, bit 0. If you were addressing a byte, memory byte 0. If you're addressing it as a word, memory word 0. Integers are the same because integer and a word occupy 2 bytes, so they're both technically a word length of information. And then double word and double integer, you just replace the W with the D, and you'll see how this notation relays to addressing information in the PLC in a second. You'll see here that for the bit, byte, word, integer, double word, they give you the possible value ranges for that as well, just as a kind of a summary of what I had just talked about with all those different lengths of information. There are also data block memory areas, which I'm going to speak about as well. And for direct addressing in a data block, say for example your data block's data block 1, the addressing for a bit would be data block 1, data block byte 0, bit 0. If you're looking at a byte, data block 1, data block byte 0, and so on and so forth. The notation is rather straightforward once you start to look at it. So how does this relay to tag values in a PLC? Well, I'll show you that right now. I'm going to pull this over and pull this up. So this is the first project I'm going to be showing you guys. More or less, I already added a PLC to the project using the add new device function. And there's already a bunch of pre-made functions and a main organization block, which I'll explain in a second. But quickly, I want to show you how I, Q, and M and data block memory areas relay to information in the PLC. So you'll see here in our PLC tag table, this is where you define your global memory areas. You'll see that there are a bunch of tags, and they're assigned to a specific tag table, and they have this particular data type. So you'll see that these are all Boolean, and these are all global memory bits. So this is a memory byte 3, bit 5, memory byte 3, bit 6, memory byte 3, bit 7, so on and so forth. If you're using I or Q memory, the addressing would be the same exact, except rather than M, you would use an I and Q. I address memory area is typically going to be associated with the inputs of your PLC or inputs from a separate device telegram if you're mapping information to and from separate devices. So, for example, our global I address area in this specific project is associated to the inputs on the PLC. So if I actually pull open the PLC here and I zoom in a little bit, and I focus on the PLC, you'll see that on the inputs, the first byte is located to the first 8 inputs, and then there are 6 individual bits in byte 1 of the I address area. And the converse is true with the global output area. Usually they're assigned to outputs from the PLC or outputs from the PLC to an input on a separate device. That's more or less how the I and Q address memory areas work. And usually you will define those in your PLC tag table right here. I don't have any I or Q addresses used in this. However, I do have other projects where I'll be able to show you that working. So for Siemens PLC, main organization block 1, which I'll show you here in this graphic. Main organization block 1 is the interface between the user program and the PLC's operating system. So what happens here in a typical scan cycle for a PLC is that the PLC will turn on, it will scan the inputs to see what inputs are true. It'll start running the user program starting with organization block 1, and it'll scan from top to bottom and left to right. So it'll check the inputs, it'll run the user program and run any functions. So in this specific case, OB1 will start, function 1 will say is a network 1, so it'll run function 1. When function 1 ends, it'll go to function 2, and then function 3, and then once it completes all the functions or function blocks within inside your organization block, the scan completes and updates all of the Q addresses. So scans the inputs, runs the user program, updates the outputs. That's more or less how the scan cycle works with the Siemens PLC. That being said, organization blocks, like I said, are the interface between the user program and the PLC's operating system. And there are different types of organization blocks to achieve different things. Organization blocks interrupt based on the numerical value that they have. So for example, yes.
I'm sorry to interrupt. Ben just asked, could you explain the word image in that previous diagram?
So essentially, the image is where you store the values of your inputs prior to the scan. So for example, when the scan starts, it checks all of the inputs that are lying in the process image input. More or less, it's a query for the inputs, so that, for example, if this checks the I image area, the global inputs, it runs the user program. There may be inputs that may go true while it's scanning the user program, so that on the next scan, it'll see those images or those bits and bytes of information true or not true in that image area before scanning the program again. That's more or less what the process image input do and the process image output do, is they hold the residual values of I and Q addresses while the PLC is being scanned. Does that answer your question? I cannot see the...
He said yes.
Okay,
yeah,
awesome. So like I was saying, organization blocks are the interface between the user program and the PLC's operating system. And I want to show you here, even though I do have this project open, I can open a reference project to view other code. And that's just how I figured to be the easiest way to show you all the organization blocks. So we're in the user program for this project. You can see that in your folders, you can label and create folders for different types of blocks that you're going to be using. That's more or less secondary to what I'm going to be showing you. But the idea here is that you have your main organization block. And if I were to open this, you'll see that there are functions embedded in it in network 1. So if OB1 was continuously scanning, it would be continuously scanning these functions. And then there's these other organization blocks that are used to run pieces of code when particular things happen. So for example, if I were to go and add a new device, I can show you what these other organization blocks do. I'm sorry, if I were to add another block, I'll show you what these other organization blocks are designed to do. So say you're adding in another organization block outside of OB1, there are a whole plethora of different OBs that can be used for different tasks. You'll see there's a startup OB with a number of 100, so that when you start up the PLC, this is a higher value than OB1. It's OB100. It's a higher numerical value. So say the PLC started up, it would run OB100 first, and then it would continue down the ladder of different OBs, depending on if they're called or not, because while this is called at the beginning of the PLC starting, some may not happen every cycle. Some may happen, like for example, at a certain time or day. Some may happen cyclically during the program running. You can have OBs that will interrupt the main program when a piece of hardware is pulled out of the rack. You can have OBs, like it says here, if the time error interrupt occurs, if the OB will interrupt cyclic program execution if the maximum cycle time has been exceeded. So you'll see that there are different organization blocks that can be used to handle your program. More often than not, people don't use all of these. You can if you want to. They're not always necessary, but it really depends situationally on what you're going to be achieving with your program. I do have a good graphic here, if I could pull it up, of some of the different OBs, like I was saying. OB1 is constantly scanning your program. If you have a startup OB that, because it has a higher value on start, will run first and then run the actual program. But like I said, there are also OBs that will interrupt the program based on what's going on: time of day, cyclic interrupts, time delay interrupts, hardware interrupts. And then there's also OBs that may or may not run when an error occurs in the user program. So I wanted to quickly explain organization blocks and how they function, just because I'm going to be talking about all of the different instructions that reside in a ladder logic program with Siemens PLCs. It made more sense to me to explain those first before I went in and started to explain functions and individual operations. So this is a program, like I said, that more or less has a function correlated to each set of instructions that you see here on the instruction tab, if you will. So I'm going to be going through each one of these and kind of showing you what the functions are. And for those of you that are not familiar with Siemens, there may be things that you might see that are familiar to you in the Rockwell world, but you also may see things that are familiar to you in the Siemens world. It really depends. So this is the main OB1 for a separate project, so I want to close that. This is the main organization block for this program. And you'll see here, network 1 has function 1, network 2 has function 2, 3, so on and so forth. Like I said, PLC program is scanned from top to bottom, left to right. So this would be the first thing that would be scanned. This area right here, I should have mentioned this earlier, is the program editor area. More or less, this is where you will develop your code. And on the right here is where you would find your instructions. I'm going to go through those instructions now. You also have a favorites bar here. So if there are instructions that you use on the regular, you can pull them right into the favorites bar so that we have easy access to them. So to display all this functionality, I'm going to use something called PLC Sim, which is something that comes with any Step 7 licensing and is more or less an additional software package to TIA Portal. So I'm going to simulate my PLC. That way I can mimic it real time as if it were actually as if there was a real PLC in front of me processing. So I'm going to click on the PLC and I'm going to start a simulation. It's going to pull up this this wizard here, almost as if I were to be downloading to a physical device in front of me. It's going to ask me to search for the PLC simulator. Once it sees the PLC simulator, I can then download the program to the simulated PLC. Once the download completes, you'll see that I can go online with the PLC to compare what's online with the PLC and what's offline with the PLC. So this is a good way to check if a program that you have offline matches the online PLC program. For those of you that may be using this functionality or may be going online with a PLC and need to tell if there's differences between online and offline. So now that we have a PLC simulator up and running, we can go online with this program. And once we go online with this program, you'll see in this project tree area that it'll show a bunch of green dots. Green dots are good things. That means that the online and offline program match one-to-one. If there were differences, you would see a blue, half orange circle saying there's differences online and offline. Now that we're on at the PLC, we want to monitor our code. And you'll do that by coming up to this eyeglass here and clicking the monitor button. And you'll see now we can tell which blocks are being processed. So the green, almost as if like it's powered on, indicates that these blocks are being scanned continuously. If one of the blocks was not green, if it was just grayed out, that would mean that it's not being scanned currently. So that being said, I'm going to hop into these operations instructions quickly.
Yes.
Hello.
Well, I was just on Evansville. They switched the system over and I had to turn on their new OPC tags because the guy did it without doing it with me. So I just was on doing that.
Okay. Interesting. So yeah, this is the first block. These are BitLogic examples. These are the instructions that you find here. It is more or less just a bunch of BitLogic as said. And this is where the global memory comes into play. This specific program seems to be using more global memory. Memory tags, these global memory tags, M memory area, are usually used for tags that that may or may not be communicating with your HMI, that may be being used to move information into a data block value to store that value permanently. And the beauty of memory tags is that we can modify them real time when we are actually testing out our logic. You'll see here, this is Q output address byte 0, bit 0. That correlates to a tag almost always because usually a coil, when it's turned on, is turning an output on your PLC. So that makes sense why it is associated to an output on the PLC. If you were using a sensor like a photo eye of some sorts and it had I address byte 0, bit 0, that would be here. And every time that photo eye would see something, it would close. Therefore, you know, if the rest of these close as well, it would turn on this coil. More or less, this whole function is built around the idea of BitLogic operations. I'm going to quickly go through all of these because this could take a long time if I don't. So this is more or less a large AND sequence. If this is true and this is true and this is true, this output will be set true. Pretty self-explanatory. This is a parallel branch circuit. So anything that is in series is ANDed, anything in parallel is ORed. So that more or less explains itself. If this is true and this is true, then that will set the output true. That's more or less how an AND OR statement works. There are inline operations like this not instruction. You'll see here that even though this contact is not closed, this bit is not closed, it's not true. That's the whole purpose of this. When it sees nothing on the rising edge, it sets the output true. And if I were to set this, modify it to a 1, it turns off the output because that's just how this not function works. There are also coils that can do the same thing, which is something I think more Allen Bradley folks are familiar with. I think coils often have that functionality rather than being independent. This does the same exact thing. When this is not true, the output is true. So now that this is true, it's off, more or less. There are set and reset coils. So if I use this tag to set output 0 for true, I'll do that right now. You'll see that it sets, and when I unmodify it, it stays set until it sees it reset. So it's set here, and you can see that this tag and this tag are used in the same place, except this one is a reset coil. So when I modify this to 0, it resets any coils that have this tag associated to it, more or less. There are functions that can set multiple bits true at a time. That's what this will do. If this were to go true, it sets this memory area, and it sets 4 bits in that memory area starting at this point true. And there's also the option to reset a set of bits using this function. There are latches, so these can be used for various things in different applications. I'm not going to go into detail. This is a reset dominant, so even if I set this true, it'll set the output on, but as soon as it sees the reset held high, it'll set the output off. And you'll see that that stays true even when the set is on, so the reset is dominant. I gotta get used to these functions. The opposite is true with the set reset. The set overwrites the reset in this instance. I'm not going to simulate that. There are contacts that you can have that are positive edge one-shots. And more or less what that means is that when this tag goes true and it sees a rising edge, when this tag has a rising edge, this will pulse on and set this output true. So if I were to do this, you'll see this OS memory, which is essentially storing the last cycle's value, will go true. So when I modify this to a 1, it sees a rising edge and it sets the output. It happens so quickly you can't see it, but you'll see that the OS memory tells the story. It saw a rising edge, so it's holding the previous scan's value, which means that this was true in the previous scan. And when I turn it off, you'll see that that flips to a false. It's also the same with the negate pulse. When it sees a falling edge on this tag, it'll one-shot to the output. Now these one scan positive edges and one scan positive edge and one scan negative edge can also be done for coils rather than being done on the contacts. And there are also individual instructions that you can use that will decouple from contacts and coils. This more or less just does the same thing as the pulse contact does. So it sees that goes true. The OS memory holds that value and remembers it. And once it sees a 0, it scans again, and then it updates and sees that it's a 0 because it is a 0. And there's also an operation for negate triggers. So there are timer instructions. Probably should open all these first, but we're just going to run through these real quickly. Oops. You'll see there I accidentally clicked on the program, so I created a discrepancy online and offline, which is what you just saw. There are pulse timers, so if this were to go true, this will pulse on for the preset time of 5 seconds. There are on delay timers, so if this were to go true, it would wait 5 seconds and then turn on after that period of time has elapsed, setting this output on. There are off delay timers, so if this were to go true, it would stay on for 5 seconds and then turn off after that 5 seconds. There are time accumulators. So you set a preset time, and if the input goes true, that timer starts to count up. You'll see that this has already reached its threshold and set the output true, so we want to reset that quickly. We'll set that to 0, and I'll show you how the accumulator works. If the input on in goes true, it'll accumulate time up until it hits that PT, preset time, and then once it hits that preset time, it sets the output true until it sees a reset. And I'll turn these off quickly. They're used for several blocks, so I don't want to create something on accident. Now, this is another on delay timer, but if you notice with all the other timers that we've been using, they have hard-coded values into the preset time. Now, this block specifically is using a data block tag. And for those of you who don't know, I kind of explained IQ and M memory. They have global validity. Global data block values also have global validity. And the difference between these tags and the PLC tags is that they can store values and they can be set as retentive so that if a value changes and a power cycle occurs, it'll save the most previous value. You'll see here that this data block and the global time preset, this tag is in this data block. And the main difference that I'm trying to show you here is that if I tried to change any of these other hard-coded values, it would create a discrepancy online. So if I click on this and I go to like 3 seconds, for example, did that take it? The point I'm trying to make is if you were to try to change this, you would see an online-offline difference, and then you'd have to re-download to the PLC. Whereas if you're using a data block value, you can modify its preset value, or you can modify the value of that tag without having to re-download to the user program. So if I just change this to 3 seconds, for example, you'll see it's at 5 seconds now, but as soon as I change that, it changes the time value without having me re-download to the user program, which is pretty nice if you're trying to test things on the fly without having to re-download to your PLC. So there are also counter instructions. And I accidentally clicked on something again and created a discrepancy here. This is great for showing you guys, but I'm not trying to do that. So there's a count up timer, or sorry, there's a count up function, operation, whatever you want to call it, every time it sees a rising edge at CU, it counts up. And once it hits the preset value, it'll turn the output true. If you wanted to reset this value back to 0, you could do so by turning on the reset. There's a countdown timer, countdown operation. It does the exact opposite of the count up. And then there's an operation that does both count up and count down. More or less, this causes the counter to count up. This causes the counter to go down. This resets the counter. And if this hits 0, if you set this true, it sets the counter to the lower value, which in this case would just be 0. Obviously, once you hit, once you surpass your preset value with your current value, it sets the output true. There are also comparative operations. I'll go live with this. So you'll see there's a whole bunch of different instructions for comparing two separate values, and you can see them here on the right-hand side. So this whole first line is using equal. So if this is equal to this, the output will be set true. If this is equal to this, the output will be set true. In this situation, all of these two tags would have to be true or equal. These would have to be equal. These would have to be equal, and these would have to be equal to set this output high. The point of showing 4 separate equal operations is that you can use different data types. So this is specifically comparing integers. This is specifically comparing double integers, real values, and time values. The opposite of equal operation is not equal to. So when this is not equal to this, it sets the output true, which is currently happening. You have greater than equal to, that's pretty self-explanatory. If this is greater than this, the output will be set true. Whereas if it's less than or equal to, which is good, it'll show you that it works. When this is less than this, it'll set the output high. So this is negative value, this is a positive value, it's clearly less. If this value were greater than this value, it would set the output high. Same with the less than, it's the opposite. If this was less than this, it's set the output high, which it's doing right now. There are operations that check if a value is in range or out of range. So they're both looking at the same global data block tag here. This is clearly not in range. That's why this is not on. And this is clearly out of range, the same tag. So that's why this output is true. There are operations that check if a value is a real value or not. This is a real value clearly because it has a decimal place. So it is true. It is not a valid real number. And if a value was if it was not a valid real number, this output would be set true. But since it is a valid real number, it's not setting the output true. Like I said, this was something that was typically designed for a lunch and learn, but I felt like it was important to show everyone, especially because it's not often you get to work with all of the different operations that Siemens has, or any vendor for that matter. It's not often you get to see all of the program operations work. I accidentally clicked something there. There are mathematical functions. You can create your own equations here and then define the inputs, and that'll calculate that. It'll perform that equation or calculate that equation. There are instructions that add values. So if this were to be true and this block was to be processed, these two values would add to equal this, and then so on and so forth. Continue to add. There are subtraction blocks, which do the opposite of addition. You guys all know this. I'm not going to have to explain this. Multiplication, division, modification function gives the remainder of a division. This turns a value from a positive to a negative. I'll type a 1 in there, and you'll see that that works correctly. There's an increment function. So if this were to go high, it would increment this value defined at the input here. Boom. Oh, it's held high, so it's continually incrementing every scan. However, if it were just a pulse, we'd usually use a pulse for this instance. That way it would see that true rising edge, it would pulse once, it would count by once, and you're good to go. I should try change that at some point in time. Same, there's a decrement function that does the opposite. You can take an absolute value of a number. You can get the minimum of 2 values. Clearly, in this case, 0 is less than 1. You could take the maximum, 1 is greater than 0. You can limit a value to a minimum and maximum value. Clearly, this is more negative than it is positive, so it's closer to the minimum threshold than it is the maximum. You could take the square root of a value, or sorry, the square, and then you can also take the square root. The natural log, I'm not going to explain all these. I'm sure most of you understand what an exponential value is, taking the sine, cosine, tangent, and then their arc sine, arc cosine, arc tangent functions. I don't need to explain all those. For those of you that understand trigonometry, then these will make complete sense. You could take a fraction of a real number if you needed to. And then there's the exponentiate function. You can exponentiate function to raise the value at the one input power specified with the input 2. So anything held to a 0 power is 1, which is why that's showing a 1 value. If this was 1 to the 0, it'd be the same thing. If it was 2 to the 2, it would be 4. So, you know, it's pretty self-explanatory. There are operations that are used to move data. And let me simulate this. This is pretty self-explanatory, but I'm going to show the data block tag side by side with the program so that you can see these values in the data block change as these functions are calculated or run. So the data block, you can also go online with the data block, just like the tag table, just like your blocks. You can go online, you can monitor the real values versus the start values. And we're looking specifically at math integer, which is an array of 32 values. So the move instruction is pretty simple. It takes this value and moves it to this value in this tag. So integer data 0 would be moved to math integer value 15. I must have already wrote that in at some point in time because it's already there, but there's some other instructions that I'll do. I'll actually I'll have the PLC scan, that way you can see the values change. So the field read is pretty self-explanatory. When this goes true, it'll look at this value, math integer 1, and it'll offset by 10 values, and it'll copy those. It'll read those values to the global data block starting at integer data 1, so this tag specifically. There's also the opposite of writing values. So you can, if this were to go true, exactly what it says, it writes a value to an array offset by an index. There are operations that move values in masses, basically, starting with global productions totals 1. We'll show that, for example, and counting by 3. So 1, 2, and 3. More or less when this block is processed, so I'll make this a 1. I'll make this a 2. When this block is processed, you'll see that it's going to take this tag and then the 3 following values here that I just changed in this data block, and it's going to push them to this tag starting at that index. So production totals 12. So when I run this instruction, it should move 1, 2, and 0 to 12, which I guess you guys can't see, which would be right here. So it would move 1, 2, and 0 to here. And if I perform this, you'll see that that happens in real time. There's also a move block interruptible, which is more or less what it sounds like. It cannot be interrupted. It's the same operation as this, except if something were to write to the same values at the same time, you wouldn't be able to interrupt this block if it were processing. You can fill a block with a data value and then offset by a specific count. So looking at this tag, its value is negative 32,768. If we were to open integer data, it's actually, that's just it right there. Starting at math integer index 20, which is here. If we were to process this block, I know those values are already here, but if we were to process this block, we would take this value and then we would write to 10 values in an array starting at this point. So I know it's already there. I guess the only way I can show you is to change one of the values and then overwrite it. So if I were to do this, boom, you'll see that it overwrites and pushes that value into 10 indexes starting at this tag. And there's the same thing with the move block. There's also an uninterruptible version. And that's, I'm not sure what the specific use case is for that, but exactly what I said earlier, it cannot be interrupted if it were to be processed. Swap does exactly what it sounds like. Swap operation changes the order of the bytes within the tag. So basically swaps the least significant octet with the most significant octet. It just like flips the byte basically. Okay, there are conversion operations that you can use. And we're already at 11:30, so I may go a little bit longer. You can convert values using a convert block, and you can define the data type you're going from to. In this case, this is going from integer to a real, so clearly an integer doesn't have a decimal place, and it's turning it into a real value that has a decimal place. You can round a value. So for example, if I took 0.4, or sorry, like 1.4 or whatever, it would round to the nearest whole. So in this case, it's closer to 1 than it is to 2. There are functions that always round up, like ceiling, functions that always round down, floor. Truncate the function. Truncate the function will always, geez, I'm drawing blanks on that right now. Essentially, it always pushes the function back to 0. I think that's what it is. I'm trying to remember specifically. It pushes it closer to 0, depending on what the value is, I believe. So if it were, even if it were like 4.9, it would push it to 4. Yeah. You can normalize and scale values, more or less normalize. You define your minimum and maximum, and then your actual value. It essentially takes whatever this range is that you give it and pushes it to 0 and between 0 and 1, which makes it a percentage, basically 0 to 100%. And then there's scaling. You'll see that they scale this value between 0 and 1 to a percentile, and then they scale the lower bound 0% to 100 and the higher bound 100% to 500, so which more or less manipulates that value. We're almost done here with these program examples. Then we'll hop into functions and function blocks quickly. So there are program control instructions, which can be seen here. The jump function is pretty straightforward. If this were to go true, it's going to jump to where you see this memory value here, which is network 3. So if this were to go true, it would skip network 2 and jump right to network 3. But if this were to never go true, it would scan it chronologically and never skip anything. This is just ways that you can control your program that I haven't specifically seen them used in applications, but I'm sure they are. There's also the return statement. So more or less return statement, it cuts power flow and exits the block. So if, for example, the scan got to network 4 and it saw this go true, it would stop scanning there. It would exit the block and go back to OB1 and continue scanning top to bottom, left to right. Logical operations. Select this more or less depending on if this value is true here. So if this is not true, it selects value 1. If this goes true, it selects value 2. Pretty self-explanatory. Multiplexer, more or less K is the value that is looking at the number of the input. So right now it's set for 0. A multiplexer, basically, if this were to go true, depending on the value of K, it would move said value to the output. So since it's looking at input 0, which is 0 right here, it moved that to the output. Whereas if I modify this to a 1, it's now moving 6 because 1 is input 1. So that's what a multiplexer does. It moves a defined set of inputs to the set output based on the value of K. And if you surpass the maximum amount of inputs that are defined on this block, because you can expand if you'd like, it'll just move whatever else this value may be. So if, say, for example, it were input 4 that K is looking for, input 4 doesn't exist. So by notion of this, how this operation works, it would move else to that output. And then there's the demultiplexer, which does the exact opposite. It moves a set input based on a value of K to the output. and that output can be expanded as well just by clicking on this little starburst. And I'll show you that real quickly. If I were to click it, it adds another output. And we'll exit that. The last set of operations before we talk about something else are the one pulse to aid in expanding shift functions. Okay. I'm not going to go through this because of the set of time we have, but I'm just going to explain more or less what they do. If this were to go true and this pulse were on, if I were to show the data block values, oops, let me close this. Math integer 21. The shift right function essentially looks at the value you're looking at here. So usually you have your input and your output are the same tag in this instance usually. Shift right takes all of the bits in that data value and rotate or shifts them to the right bit by bit. So because this is defined as this tag and we're set as 1, it's going to shift everything in that tag. So for example, this is an integer, so there would be 16 bits. It would shift each one of those bits to the right by 1 value, which is more or less what this does. Shift left does the exact opposite. It takes all those bits, shifts them to the left by 1, or whatever you decide to specify that as. This just gives you some different ways that you can manipulate bits within a tag. Same with rotate right and rotate left. Rotate right, it kind of does the same thing as the swap function in the sense that it rotates all the values in a bit. Say for example, we had a byte 8 bits, it would rotate all those values to the right and like kind of flip them. And same with the rotate to the left, it does the same thing. It swaps bit by bit from the right, or sorry, for this rotate right, it would do everything to the right. Rotate left, it would move everything to the left, and rotate to the left. So that more or less, in a nutshell, is almost all of the instructions that come with TIA Portal and Siemens PLCs. And this program itself is really nice. Just as an example, for those that are not familiar with all the different operations that exist, I'd be happy to send this to anyone that wants to use this as an example, or someone wants to dissect this and try using each of these functions with the setup data block that I have. I'd be happy to send that to anyone who really wants to take a look at it. This is great for showing people that are new to Portal and ladder logic, how it works, kind of. So that being said, we explained what organization blocks are. We walked through what all the instructions are in relay ladder logic. We talked about PLC global memory areas and data blocks. And we also talked about how a scan typically works with the Siemens PLC. So that being said, we're going to move into functions and then function blocks. For those of you that are familiar, I'm going to open this. Functions and function blocks are very similar in the sense that they are usually subroutines for whatever your program, for whatever sub-process that you have in your program. Actually, I already have it open here. So functions are subroutines, and essentially you can use functions to control different subroutines that you may have in a particular application. I have a project here that's pulled up, and inside of it, we have the main organization block 1, which is open. We have tank 1 controls and tank 2 controls. And inside of tank 1 controls and tank 2 controls, there is another function called pump valve. And there's a star next to the name because it's being used multiple times. So I'm going to walk through what exactly a function is and how it differs to a function block. So there's global memory, I, Q, and M, which is valid throughout the entire program. There are also local values that are local to the block that they're defined in. And specifically, this pump valve block that we're looking at has a bunch of local tags that are defined in it. They are only valid when this block is processed. So you have inputs, start, stop, where you can define your data type values. You have outputs, And then you have in-out values. Inputs are pretty straightforward. They are only read. Outputs are obviously only written. In-outs are read and written in a block. And then there's temporary values, which are only valid during a block call. Once the block starts, that value is what it is. And then once the block is finished scanning, that temporary value is gone until the next scan. Constants are exactly what they sound like. You can type in a tag here and assign a specific value to it, and that will be just a set value. You'll notice that in this block, using these local tags have a different notation than global tags. They have a hashtag or a pound in front of them, which is usually how you would denote if a tag is a local tag, because global tags, if I were to open the PLC tag table, or if I were to open up a, for example, tank 1 control, global tags have address, actual addresses, whereas local do not. So more or less, what you're seeing in this pump valve block is, give me a second to pull this up, is this. And I'll try to show you both of these at the same time. It's not the easiest. So we have OB1, network 1, we have tank controls, and network 2, we also have tank controls. Inside network 1, inside tank controls, we have pump valve. But if we were to also open up tank 2 controls, we also have a second pump valve instruction. You'll notice if I compare the two by splitting the window here, they're the same exact function, but the defined inputs and outputs have different address areas. So this is just a great way for you to develop a block of code. You assign a bunch of local tags to that block of code, and you build the block of code with those local tags. This allows you to take that block of code, to move into a library, to use it in a separate program. Because if you had used these actual global memory areas inside of pump valve, for example, you would need to make sure that the setup you're going to be using this code on again would have the same, the start button would need to be wired into the same spot. The stop button would need to be wired into the same spot. So using local tags within inside a function like this is just a way of creating code that is reusable. And I'll show you what I mean by that in a second when I create another instance of this. But I just wanted to show you that I am calling this twice, and I'm using different addresses for each block. So this is tank 1 controls. So it's using start 1, stop 1. Timer values are for the first tank, and same with the outputs for the pump and the valve. And if I were to look at the second block here, the tank controls 2, you'll see everything is set up for the IO for that second tank. I have a good, if I could pull it up, I have a good graphic here that kind of breaks down the scan cycle with this exact setup. You have your process image input, which checks the true input image values, starts the scan. We're in network 1, where function 1 exists, tank 1 controls. Inside of tank 1 controls, we have that pump valve, which is this. So you'll see that it goes in, starts the scan, it sees function 1, starts scanning that, and inside start function 1, it sees pump valves control. Once that finishes processing, it goes on to function 2, which is tank 2 controls, and then it scans the specific block for that pump, and so on and so forth. And this is kind of the idea behind the code that we have here. So I'll show you this in the actual program. So I'm going to close tank 2. We're in tank 1's controls now. We're going to open up the pump valve block that's specific to this. You'll see everything's defined in local tags, like I explained, which is defined up here. If this were to start, I guess I should simulate this. I'll simulate it now. Like once again, if you're going to simulate something, you need to highlight the device you're looking at and then click the simulate button. More or less what happens here, when the start button is clicked and the e-stop is not pressed, I'll explain that in a second, sorry. So an e-stop typically, physically, has contacts that are normally closed. So even though this is a normally open contact here, because the e-stop's not pressed and the contacts aren't open, this will be closed in the program because the actual physical contacts are closed. So we'll pretend this is closed as if the e-stop wasn't pressed. When you click start, it will turn on this flag, which will ultimately set this bit, which is more or less just like a means of having a dog chase its own tail. Once this is set true, this sets this high, and as long as the stop's not pressed, it'll stay true. So that way you can press the button once, it stays on, it kind of latches itself almost. You don't have to press the start button again. But once the run flag is true, on delay timer starts up. So it turns on, waits 5 seconds to turn on, and then it'll turn on the pump. You'll see here on timer, when that output, that's what the Q stands for, is true, it turns on the pump. Whereas when the run flag also happens, there's also an off delay timer that happens. So it waits, it turns on for 5 seconds and then turns off. And when that is true, it'll turn on the valve. Valve starts immediately shuts down after the delay, which makes sense. This is just a means of showing you how this block is actually working, and how you can use that same piece of code in several blocks to control, separate pumps if you had separate pumps. So let's pretend that we wanted to add a third tank and a third pump to the actual setup here. I'll do something like this. I'll just copy and paste tank 2 controls. I'll rename it to tank 3 controls. And then inside tank 3 controls, we still have this function 21, which is being called, which is going to control pump 3 for tank 3. But you'll notice that the I/O, the inputs here and the outputs here, are still set up for the second tank. I'm going to show you something useful here. Under tasks, we want to change out all of these tank 2, pump 2 values with tank 3, pump 3 values. So we want to find 2 and we want to replace it with 3. And this is just an easy way of replacing everything quickly if you already have the tags built for them. So I'll, for example, replace the first one, start, stop 3, replacing the timer values, as well as the run flags and the output tags. And you'll notice, like I said, this only works usually, this will work if you don't have the tags defined. You'll just have to define the tags once you create them. But in this case, you'll see, like, for example, there's no data blocks that exist for the timers for pump 3 yet. So we'd have to define them in some manner so that the program knows what exactly we're talking about. I'd have to recompile it, and then you'd see these data blocks appear. But basically, if a tag doesn't exist or a block doesn't exist that's being addressed, then it'll give you these little, this red indication that something's wrong here. What I did wanted to show you also, I'll remove this for the meantime. Yes, do. If we go online with this, this is real helpful if you have a function like this being used for several pumps. We can open up the block that's being called multiple times, and if we're online with this, we can actually look at the instance that we're calling here. So right now we are looking at tank 1, pump 1, and pump 1 specific call. Whereas if we want to look at tank 2, pump 2 specific call, we can come over here to change the call environment, and then we can take a look at the specific call that we want to. And then, depending on how the process is occurring for that specific pump, this will be acting differently than it would be in the other instance, if that makes sense. So functions are subroutines. They can be called multiple times as long as they are defined correctly with local variables. The difference between a function and a function block is that a function does not have an allocated memory area, whereas a function block does have an allocated memory area, a data block, if you will. So I'm going to open a project here that shows this. You may be asking yourself, why would there be a function, or in this case, a function block that has a designated memory area? And the question's pretty straightforward. Say you had a function, kind of similar like to the pump block that we had, except it's a function block now, and there are a specific set of parameters for each pump. you can use the associated data block for each one of those pump calls to store data regarding that pump. It's just a means of having a preset of properties for different pumps, because not every pump might be the same. It might not have all the same parameters that the other pump may have, and you'll see what I'm talking about exactly in 1 second. So we want to go online with this. And if we open the program blocks, you'll see here we have main. This is set up very similar to the last project. We have function 1, which is for system 1, function 2, which is for system 2, and function 3 is for system 3. If we were to open system 1, for example, you'll see inside here there is a whole bunch of logic. The main thing that I want to show you all is that there is a motor block for each system, and for each motor block, which is a function block, there is an associated data block for that specific function block. So this is system 1's data block. So if I were to open up its corresponding instance database or instance data block, and I were to go online with it, these values would correlate to this specific call of motor block. Whereas if I open up, for example, system 2, I'll just compare them side to side so you can see them. The motor block is also being called again. It's being used again, except this time you'll see here for motor block 1, it's looking at this specific data block for pump A. But now the motor block is referring to the data area for feed pump B. So inside of this data block for this specific call, you'd have a unique set of data to that call. And the same applies to pump C. In system 3, you'd also have another motor block that's called that has an associated data block. And if I were to open up motor data block, for example, or motor block, maybe I missed that. You'll see that this is set up the same way as the other function that we'd seen in the last project, how it's being called multiple times, because everything is defined in the local variable area, and then the program, or this block specifically, is all built with local tags, which makes it reusable. Like I said, if you were to use global memory addressing in this, it would kind of make the code unique to one application. You wouldn't be able to use it in several applications, but because this is set up with all local tags, if you were to look at the actual function block, you'll see this is where we actually assign the global data tags to the specific program. So I don't have much more time, and I know I threw a lot of information at you guys. I want to use this time now to address any questions you may have regarding anything that I may have covered, because it was a lot of information. I didn't get to cover everything in as much depth as I probably would have in a normal lunch and learn. But like I said, this is the first time me trying something like this that's more programmatic based, a little bit more complicated, requires a little bit more thought. So like I said, I'd be happy to answer questions. If there's stuff that I left unanswered, please feel free to ask that question now. And I can open up different projects that we may have used throughout this so that I can address a question regarding them.
Corey,
Yes.
we do have a question.
Cool.
Could you show how to find the address of an item in a data block?
Could you show how to find the address of an item in a data block? Great question. So I don't know if this is the best project to look at for this. So this is a good topic. All data blocks, not all data blocks, more often than not, a data block is optimized. And what optimized data block means is that there are no specific addressing in that optimized data block. As the data is addressed into the actual data block, it is structurally stored by words, by bytes, by bits, so that essentially imagine you're playing Tetris in an optimized data block. Everything would fit perfectly into that data block. There'd be no missing gaps, which is just a great way of optimizing and utilizing that space correctly. The downfall of viewing that is that you can't have specific addressing for the tags in that data block. You can only symbolically access it by the name that you give it here. Now, there are ways that you can create an unoptimized data block or a non-optimized data block. And you would go to the properties of said data block, and under optimized block access, you would uncheck that. And then it'll give you an offset. And I believe if I were to compile this, it would start to fill in numerical values here. Once you have a non-optimized data block like that, then you can start to address down to the bit and byte level, like I had shown here. So in an optimized data block, you can only symbolically access those tags. But in a non-optimized data block, that's when you can start to address tags by their direct address, not their symbolic address, which is what you see here. So if we were looking at, for example, I don't know if this will work if I compile this quickly. Now that I have my offsets, I can address these tags accordingly with their direct addressing. So like I showed here, if I were to address, we'll say Boolean data 0, the first one in this entire block, we would address it like, let me see if I can get this so you can all see it at the same time. Is that good enough? Boom. So say we were going to address this specific tag in this non-optimized block. Oops. Excuse me for 1 second, I accidentally clicked off the wrong screen. Now that this is not optimized, it has a structure to it. So if we wanted to address Boolean data 0, we would do so using this notation. So in this case, we're using data block 6. So it would be db6 dot db x0 bit 0, because that correlates to byte 0 bit 0 here. Does that make sense to you, Ben, on optimized versus non-optimized and how you would address a non-optimized data block tag?
Yeah, that makes sense. I was working with the optimized data block, so that's why I didn't see that offset.
Right.
Thanks.
No, yeah, it's not something that's exactly obvious. It's Siemens did the optimized data blocks just to save you work memory area in your PLC, but they wanted to give you the option to also do this direct addressing, because there are definitely instances where you need to do that if you're going to be addressing a bit within a word that is in a data block, for example. So
yeah, we have another application that wants to talk to that data block and read data out of it, so we need that address. So
Gotcha.
Thanks for explaining that.
Absolutely. Will this recording be able to watch again? Da, da, da. Like I said, I know this was a lot. I will take this project here, the one that has all of the operations or instructions, whatever you want to call them, used in a program. That way, if you need to go over them and how they function, this is a great way to do so using the simulator. This is probably the most pertinent example for all of you to use. So I will have this included in the attachments that are sent with the presentation. If there's anything else that you saw today that you might want to take a look at, like the different projects that cover the organization blocks, the functions or function blocks, we could also send those to people as well if you'd like. And I have the presentation if you'd like to see that as well. So we'll make sure the presentation gets sent over with the recording and that specific project, so that people can take a look at all the different instructions that exist for ladder logic. Now there are, obviously third-party instructions that you can add in that are not native to the Siemens TIA portal, but that's a topic for another story.
You have time for another question, Corey?
Sure.
If I have an application that I want to test with the PLC sim, is there a way I can make a script of inputs and outputs that can interact with that PLC sim?
Are you saying
Siemens.
like I address area, like I inputs?
Is there a way I could write a test script that I could tell it and give it this input address, it would set that, and then watch for a response on an output, for example?
Yeah, the only way
Siemens
you
have any programs like that?
the only way you can do it is by creating a simulate function and then building logic to simulate what exactly you're talking about. The only other way that you can simulate an input or an output is through a force table. So the reason I used all those M addresses in this program here is because I can modify those on the fly. Whereas if they were I addresses, like for example, I 0.0, the only way I can modify that to a true is if I do it from a force table. So either you have to
Do it from another function.
I see what you're saying. Like
function.
you're trying to test this like I address in the PLC program without having to use the force table. Is that what you're saying, basically? I think that's what you're saying.
Yeah, I want to do it. I want to be able to automate some of the testing. Yeah, I think I could do that with a test function.
Yeah, I think you would have to, what you'd probably have to do is you'd have to have a line of logic that simulates that input going high. So you'd probably have to do something like, I guess I could just do it here in the main organization block. We'll do it down here. We'll pretend this is, I think how you'd have to do it. Because you have to have a way to set your input true. I don't know if it'll let you do this. I have done it before, Ben. I'm drawing blanks on how I've done it because I know what you're saying. You can't just like this isn't good. This will work.
Yeah, if it was an M tag or a data block item, I could set that from a function.
Right. Yeah, I think that's that's one way of doing it. If you want to just replace those I's with memory tags in the meantime, you could do that. But I think you can also do this. You can also manipulate the program to set a input true, because you can't I know it won't let you do this, for example. Like I can't add input 0.0 and do the modify like I would if I were online with a memory tag. I think I have to set it and then reset it elsewhere in the program to simulate it that way. I don't know how else you would be able to do it, but let me take down your info, Ben. I might have a project where I had done that. I have to check back. I think I do actually. So let me take note of your info.
Yeah, I just wondered if Siemens might have another product that does that, because it seems like something that people would want to be able to do, before they download a new program to the hardware.
Right.
Some kind of test.
Yeah, the only way I can think of doing it is either having a bunch of switches wired into your inputs, or you create a subroutine inside of your program that simulates your inputs going high. That's the only way I can think of doing it. But like I said, I know I have a project somewhere. I have to dig it up that does, I think, exactly what you're looking at. It would require you to download to the PLC, which is the only downfall. If it's something that's currently running, you might not want to download. It's a software change, but either way, I think you'd have to simulate it using a subroutine, to say the least. And I'll take note of that, Ben, as well. So I'll find the relevant project I have that does what you're talking about, and I'll send it to you.